Okay, so the function's established as some sort of quadratic. Just reviewing how to find values of functions, we'll find f of 2 to start. We understand that 2 in here is the x value we're basically plugging into the function. So anywhere we see x is up here, we're inserting that 2 in. When we do that, if we spell out all the work, we've got 3 minus 5 times 2 plus 4 times 2 squared. At which point we consider our dear Aunt Sally because we're using the order of operations. Order of operations, normally I'm dealing with the exponents first here, but really as I go piece by piece, I've got 3 minus, can do the multiplication here, 5 times 2, plus, all right, before I can do this multiplication, I do have to do the exponents, so it's going to be 4 times 2 squared. Of course, that's 4. I want to be a little lazy about it. I just make that 16. Go through and calculate. 3 minus 10, negative 7 plus 16, get 9 back. So f of 2 would equal 9. And what that means is if I actually was considering the graph of this function, and this is important for us to be able to do in a calculus class, be able to relate to the graphs. If you're considering the graph of this function, you basically know that you've got a point on it, a point where x is 2 and where y is 9. So, pretty simple review. Now let's keep that same function in mind and let's try this one. I throw this in here not because the concept's supposed to be difficult, but because negatives, signs are always an issue for us. So let's find f of negative 1. Following the same pattern as the first problem, plug it in for x, this time negative 1. I've got 3 minus 5 times negative 1 plus 4 times negative 1 squared. Calculating that out. Got 3. Watching my signs, it's negative 5 times negative 1, so that's plus 5. Over here, you've got negative 1 that I'm going to square first, which of course is 1. You're going to take that 1, multiply that 4, get 4. Adding through, we find that f of negative 1 gives us 12. So we know there's a point on this graph where x is negative 1 and y is 12. Not bad, right? So still playing with the same function. Let's find f of the square root of 3. Let's throw some radicals in there. Well, whatever we did on the previous two problems seemed to work. So let's be consistent here. Spell everything out the same way, only replace x with the square root of 3. This time it'd be 3 minus 5 times x, which is the square root of 3. And what was it? Plus 4 times square root of 3 replacing x would be squared. If you want to be consistent with your parentheses, still have parentheses there, that's fine. But ultimately, as you calculate this out, you've got 3. I'm going to take 5 times the square root of 3. There's not much I can do with that. All I can write is 5 root 3. But over here, as I square this square root of 3, radical is going to disappear, right? So 3 is going to be left. That 3 is going to get multiplied to 4. Got 12 left. Combining like terms, you've got 3 plus 12, 15, minus that 5 root 3. So there's your answer for 3. All right, just as we can plug in values, we can plug in variables. Variables represent values, so anything we did with the values previously, we can still do here. If I want to find f of a, for instance, pretty simple substitution. A replaces x. So it's 3 minus 5 times a plus 4 times a squared. There's no real calculating to be done here, just simplifying, usually with variables, but That's as simple as it's going to get. If I take now an example of a slightly more complicated expression, let's do f of a plus h. This is where it starts to get a little tricky. Okay, very easy to make some little algebraic errors. But so far all we've done, we've taken this value right here, we replaced x with that idea. So being consistent, I would have 3 minus 5, replace x with a plus h, then plus 4, replace x with a plus h. That idea would be squared. So the way I'm substituting here is never changing, right? Don't care if it's variable expressions, don't care if it's actual numbers to play with. But when it's variable expressions, as I said on the previous problem, sometimes there's more simplifying to be done. So here, if I start simplifying, I've got 3. Being real careful here with my distribution, it's a negative 5 that goes through, so it's minus 5a minus 5h. And again, being very careful with distribution over here, you got to follow the order of operations. You got to think about how you played with the values before. You were squaring everything first, right? So I'd have plus 4 that I got to wait to multiply to a plus h squared. Now if you take a plus h and you square it, it's a plus h times a plus h, right? You FOIL that out, or you remember the little form for it. FOILing it out, remembering that form, you get a squared plus 2ah plus h squared. The most common mistake I usually see here is people will leave out this part, that 2ah. Remember, that's a result of FOILing everything out. So now you distribute the 4 through. All the other terms we're just bringing down. Whoops. So it would be plus 4a squared plus 8ah plus 4h squared. And at this point I'm looking to combine like terms, but that's just not happening, is it? That is so-called simplified. For number 6, let's find the difference quotient. Still using the same function. So now I'm going to find the difference quotient. The difference quotient is something that you guys have played with in Algebra 2 and in Pre-Calc. And at this point is just another thing that you have done to work with functions. But it has huge applications for us here in calculus, as you will see here in about a month. Do we remember what the difference quotient is? Does this ring a bell? Look vaguely familiar? Okay. We have to be able to simplify stuff like that. And that's where this algebra comes in. When you look at the difference quotient, you're basically playing with the function a couple of times. You got one piece of the function there that you got to figure out. And you got another piece over here that really is just the original function itself. You got to stick those two pieces in, subtract the idea, and then usually there's some h's we can cancel out, and that's how this h on the bottom goes away. So let's play with this. Using the original function. So that quadratic we've been playing with all along. If I'm going to find f of x plus h, well, f of x plus h is really the same as what I just did right here, right? Only instead of all these a's I got in my answer, there'd be x's instead. So when you're doing these types of problems, a good rule to follow is take this first part, figure it out off to the side. So I'll relate back to what I just did on problem number 5. Take that answer and insert it in down here. So this answer we just found, I'm bringing it down. Wherever I see an A, I'm putting an X in. all of this is f of x plus h. Brought to you by f of a plus h. So first piece is in. We're now subtracting. The second piece we have to substitute in is the original function itself. So the original function, what was it again? It was 3 minus 5x plus 4x squared as I slowly run out of room here. Back on the recording, I think I'm off the screen now. That's all right. Sometimes I'm a little bit off. We've got all that now over h, which don't forget to bring that down. That h is still significant. We've pieced everything together. Pretty much we're ready to combine some like terms. And the rule again on these is at some point this h in the denominator needs to go away. So if you're simplifying correctly, everything on top, once you get the leftovers, those leftovers should only have an h in it. Okay? So look at how this all kind of unfolds. This negative here I'm going to distribute through, change my signs, and then as I combine like terms, you notice how the 3's go away, the 5x's go away, and the 4x squareds go away. So what's left? You've got an h term, an h term, an h term. You should only have h terms left. At which point, because you are dividing by h, you can basically take this h and divide into each term. As long as you're dividing into each term, it's okay. So divide the h into negative 5h. You've got negative 5 left. Divide the h into the 8xh. The h's would cancel. You'd have 8x left. Divide the h into the 4h squared. You've got plus 4h left. There's your difference quotient. So in recalling how to find domains, there's a few rules I know that you guys hopefully talked about in pre-calc, at least summarized in pre-calc, that were consistent for all the problems you did where domain was involved. And of those rules, you probably talked about things like restrictions. Maybe off to the side of the function there was something that said, okay, x has to be greater than a certain value, smaller than a certain value, between a couple of values. Do you ever see that? That is your domain. But I don't see that here, right? There's no inequality symbols, no less than, no greater than. Other things that you probably talked about were roots, in particular even roots. Pre-calc you probably dealt a lot with square roots, but fourth roots would apply, sixth roots would apply. If you got roots, you can't take an even root of a negative value, right? So that's one of the rules we got to follow. The stuff under that root would have to be greater than or equal to 0. Finally, denominators. You can never divide by 0, right? So if you ever see an x in a denominator, that's an issue. So out of those 3 big things that you probably talked about last year, do you see any of that stuff right here? I don't. So when you don't see any of that stuff, what's the domain? Yeah, domain's all real numbers. So how do we express that? If we use interval notation, it's negative infinity to infinity. Now the good thing in terms of a style of thinking we need to get used to in this class, since it's a calculus class, is relating to the graph. This is a simple line, and if I graphed out the line, the y-intercept is negative 3, the slope is 2, so I go up 2 over 1, right? There's my line. Almost connected the dots there, that's pretty good, right? When you're relating to graphs and domain, remember, the domain is describing what all the x values can be for the function to keep it real. So all the x values run horizontally. As you go left to right here, you should have all of these x values from negative infinity to infinity represented. So left to right is domain, and as an added bonus here to you free of charge, we can talk about range as well. If I threw in range, anybody know what the range would be? It's negative infinity to infinity, because range is all the y values. Range goes from bottom to top. didn't have to find that there, but in case you would have to find it on a problem, you could. All right, another domain problem. F of x equals 2 minus x squared. So I just reviewed this on the previous problem. If you see restrictions, if you see even roots, if you see denominators, you got something you got to do to find the domain, right? But if you don't see that, what's the domain? It's all real numbers, and I don't see any of those here. Say, that graphing thing was kind of fun. Let me throw that range in there again. This is a good review. I mean, after all, this function here, yeah, I know we can punch in the calculator and graph it out, but what's that look like? There you go. It's a quadratic. It's a parabola. So when you go through the transformation of this parabola that, you know, in its standard form will be right here, it's just going to flip over, and it's going to move up 2 units, right? So with what we know about transformations and these types of functions, real quickly we can figure out the graph. What's the range? There you go. You're going bottom to top, negative infinity, coming up from the bottom, up to highest value, which is 2. Now, since we're using interval notation, is that 2 included? Yes. It's a point on the graph. It's a y value that would be included. All right. Sticking with the theme of domains, let's look at number 9 here. This time the function is f of x equals the square root of 8 minus 5x. Okay, so what happens if we do have one of those 3 things that I talked about in the previous 2 problems? Now we've got that even root, right? Remember what the rule is when you're playing with even roots? Okay, take the expression out. Good. Set it greater than or equal to 0. If you make sense of this rule, you can only apply even roots to something that's positive or 0. So that's why this expression has to be greater than or equal to 0. You solve that. Subtract my 8 over. Divide through by the negative. Remember, you got to flip the symbol when you're dividing by the negative. So x is less than or equal to 8/5. If x is going to be less than or equal to 8/5, and we're talking about a domain here, well, everything to the left of 8/5 would be less than, so it's negative infinity up to 8/5, and 8/5 would be included because it's less than or equal to. And there's your domain. Take any value on that interval, plug it into this function, hey, you get a real answer back. That's what that means. All right, we'll conclude with this one. I think 10 problems is enough for the first day back, right? We'll spice things up. Here's h of x now. I know, it's more intriguing, isn't it? That's going to equal 9x over 2x squared minus 8. How do you find the domain? Denominator can't be 0. Only the denominator we care about, right? Only time we would even focus in on the numerator is if it had a root in it, basically. So x on top, who cares unless there's a root? X on the bottom, we do care. That expression cannot be 0. So we set that expression not equal to 0. We solve like any other equation. Let's do this. Let's take a 2 out. Take a 2 out. We've got x squared minus 4. That does not equal 0. If I stick with the factoring theme, because hey, factoring is a good review for us right now. You got the 2 out front. You got a difference of 2 squares, factors to x minus 2, x plus 2. Got all these factors set not equal to 0. This factor doesn't have an x in it, so we don't really care about it. We can divide it out. But these two do have x's in them, or if we set those individual factors not equal to 0, we get x cannot equal Well, 2 from the first factor and negative 2 from the second, right? So if we're writing our domains in interval notation, our domains in interval notation would be really all real numbers but those two. So if we're going to do all real numbers, we take our trip going left to right, starting at negative infinity, going up to, in this case, it'd be negative 2 to start. That's the smaller of the two values we found. And we can't include it, so parentheses. We're going to have more intervals here. You form that union, right? You pick up where you left off at negative 2 and you travel up to the next value of 2. But wait, there's more, so there's another union. Pick up where you left off at 2, and we keep going. There's your domain. Whew.